Hey guys, this is an extra video here, really the main video for the second derivative test for Extrema. So there was a short one that you were to watch as well, where Guy explains how to do it. Just a brief intro. He had some nice little graphics and stuff there, so that's why I chose to use that. And then we'll go over an explanation here as well. The concept isn't really that challenging. Hopefully you find this pretty easy. This is called the second derivative test for Extrema. So it's basically another way that we can find relative mins and maxes. It's actually not as good as the first derivative test because the first derivative test always works. This one doesn't exactly always work, but the AP says you need to know both of these tests. This one, I guess, maybe could be a little bit shorter, but at any rate, you need to know the second derivative test because you might be given a question where it just gives you the critical points in the second derivative, and it says find the mins and maxes using just the critical points in the second derivative. And if you don't have any information about the first derivative, well, you couldn't necessarily find it using the first derivative test where you look at where it's increasing, which is increasing, decreasing, decreasing, increasing. So at any rate, we'll go ahead and do a few problems here on the second derivative test for Extrema. Again, it shouldn't be too difficult with these, but as always, let me know if you are struggling with this. First thing I would need to do, I wrote a little chart here. Basically, we need to find the critical points, and then we're going to plug those critical points into the second derivative. So let's go ahead and get a first derivative. For the first one, we get 12x minus 3x squared. And to find the critical points, we set that equal to 0 and solve it. And this one, we're going to pull out a 3x. And we're left with 4 minus x. So then our two critical points are x equals 0 when we set the 3x, x equals 0, and set the 4 minus x equal to 0, and we get x equals 4. So those are our two critical points, the c's. So from there, we need a second derivative. So let's go ahead and get that. F double prime of x, you're just going to go circle back up to there and take the derivative again. We get 12 minus 6x. We don't need to find the inflection points for this. Remember, inflection points are the zeros of the second derivative. We don't need to find those. What we are going to do is plug the critical numbers, these, into our second derivative. So we're going to do f double prime of 0. When we do that, we would get 12 minus 6 times 0. So that's a positive 12. F double prime of 4. We get 12 minus 6 times 4. And that gives us a negative 12. Or, let's see. Yes, like that. So, well, now we can make decisions about if this is a min or max. So we use a little chart up here. If we got a number greater than 0, meaning positive, remember, that would tell us that it's actually concave up, right? Concave up. And if something is concave up, that means it has a relative min. So we actually got a relative min. It's kind of the opposite of what you might think. Positive, you think a big maximum number, but it's the opposite of what you might think. And then so we've got a negative that's concave down. So that's going to be a relative max. I would like you to find the actual coordinate pair as well. So the x coordinate is easy because you just plug in whatever critical number there. We had 0 and 4. So the first one occurs at 0, comma, and then we would want to plug it into the original function f of 0 to find the y coordinate. So if we do f of 0, that's just going to be 12. So 0, comma 12 for that one. And then to find the other one we had was at 4. So then we would just plug 4 into our function. And what do we get there? Let's see. Six plus 12 minus 4 to the third. It looks like we get 44. So those are two extrema. 0, 12 for a minimum and 4, 44 for a max. Obviously, just make sure that your max is bigger than your min. That's kind of generally a good thing to happen. All right. So let's go ahead and look at our next one. As you can see, these really aren't difficult. Next one, go ahead and find the first derivative. F prime of x would be 4x cubed minus 36x squared. Okay, set it equal to 0. For this one, to factor it, we'll plot a GCF again. Both of these have a 4 and an x squared, so we're left with x minus 9. I'll assume you can do that well. Set both of these equal to 0, and we get x equals 0 and x equals 9. So next thing we need is a second derivative. So let's go ahead and get that, f double prime of x. We again start back from our first derivative there. We get 12x squared minus 72x. And we don't need to find the inflection points. We're just going to now plug these 2 points in. So f double prime of 0 is actually going to give us 0. And f double prime of 9, plug that in. And I believe, let's see what we get here. I think it's 324. That's positive 324. All right, so now using this little chart, if you remember f double prime of some critical number and you get 0, that means it's inconclusive. We can't make a determination, so we actually have to go back and use the first derivative test. That's why the second derivative test isn't so good, because sometimes you go through the work and then it doesn't work anyhow. So at any rate, for right now, this is inconclusive using the second derivative test. This one was a positive, which means concave up, so that is a relative min at 9, comma, we got to plug 9 into our original function, and I think you get a really big number for that. Let's see. 4 times, well, let's see. Make sure you plug it into the original function. So 9 to the 4th power minus 12 times 9 to the 3rd plus 4. Oops. Yeah, a really big negative number here. Negative 2183. All right, so now we can't just leave this 0 though without checking to see if it is a min or max. So what we actually need to do is just go back and do a quick first derivative test. To do that, that's where you plug in numbers that are less than and greater than into the first derivative to see if it's increasing or decreasing. So I'm just going to do f regular, which is 1 prime of negative 1, and then if I do f prime of positive 1, I can tell if the function's like increasing before and after. So when we do that, if we plug in negative 1, it looks like we're going to get, I think, negative 40. So that means the function's decreasing. If we plug in positive 1, we get, I think, negative 32. So it's still decreasing. Since it didn't change signs, that means there's actually no min or max there. It just kind of leveled off and then it kept decreasing. So turns out there was nothing we could tell. All right, the next one might be just a little bit more challenging simply because it's an e function. But I promise it's not that much worse once you get past the fact that it's an e. So let's go ahead and start with the first derivative. The derivative of e to some exponent is, I think, e to the u is e to the u times u prime. So this is just e to the 4 minus x squared times the derivative of that exponent, which is negative 2x. Now you might be tempted, when you're solving this, you want to go ahead and set it equal to 0. Don't rewrite the original function yet because it's kind of already factored, if you will, for us. So just leave it like this, but then when we find the second derivative, we are going to want to maybe rewrite this a bit. So let's go ahead and set this equal to 0. Since it's already into 2 factors, you can kind of just view it as these two. Set e to the 4 minus x squared equal to 0 and negative 2x equal to 0. Second one's easy. It's just going to be x equals 0. Now for the e to the 4 minus x squared equaling 0, the thing about e is if you look at the original function, e looks like this. crosses there at 1. Well, it actually never hits 0. It never crosses. There's a horizontal asymptote there at 0. So there's actually no way to make this thing 0. You might think, oh, well, how can I make the exponent 0? Well, that's not going to work, because if the exponent is 0, e to the 0 is actually 1. So there's no way to make that function equal to 0. It never crosses 0. So that means we need to just forget that one, because it's not possible. The other way that you could actually figure this out is if you were asked to, I guess, in some way prove this, not for this specific problem, but if you were to try to solve this equation, you would take the natural log of both sides to get rid of the e, because remember, e's and natural logs are opposites. So we get 4 minus x squared equals the natural log of 0. However, that's a problem also, because the natural log of 0 doesn't exist. Because if you remember what the natural log looks like, it goes like this. It crosses here at 1, but it never crosses 0 either. So either way, you're kind of stuck in a pickle there, and that will never be 0. So we actually only have this one critical number there at x equals 0. So let's go ahead and get our second derivative. I'm just going to rewrite this first one just as negative 2x e to the 4 minus x squared. Just write it that way instead. Then our second derivative is, we do have to use a product rule here. This is sort of our first function. So the derivative of that is negative 2. Keep our original second function, plus original first function, negative 2x, times the derivative of the second, which is e to the 4 minus x squared, times negative 2x. Now, we don't have to solve this, but it would be probably easy to just rewrite this a bit, make it a little simpler. So this first thing, negative 2e to the 4 minus x squared. This one, we can actually just kind of multiply this. This becomes plus 4x squared e to the 4 minus x squared. So that's a good form. We could at least plug our 0 in now. So then we could do f double prime of 0. We'd get negative 2e to the 4 minus 0, so it's just e to the 4, plus, well, the other thing has an x there, so we plug in 0 there, it's actually just going to make 0. So it's just negative 2 e to the 4th. So this is a negative, which means it's concave down. So that tells us it is a max. Sorry, it's a little bit messy here. So it's a relative max, and that occurs at 0, comma. Remember, we plugged this into the original function. So the original function is way up here. F of 0 is e to the 4 minus 0 squared, so it's e to the 4. And we just want to leave it like that. You don't want to actually write out that number. Just e to the 4 is a good way to write it. On this one, I actually pulled up the Desmos graph here, just so you can see what's happening. It says it's supposed to have a relative max e to the 4th power, which, if you remember, e is like 2.71. So it's like essentially that to the 4th power. And if you look at the graph, you'll see we got a max up there at a little under 55. Click on it there. So 54.598, which is the same thing as e to the 4th power. So. All right, a couple quick more ones here, just to show you a little bit more what's happening. Do another one of these E1s. This one starts with the product rule. So we got f prime of x. The product rule here is just going to be the x goes away, so it leaves you with just e to the 4x plus x e to the 4x times 4. So I'm going to rewrite this a little bit. E to the 4x plus 4x e to the 4x. Just rearrange it. Now with these e's, setting this thing equal to 0, since it's not factored yet, we still want to just pull out the greatest common factor, which the GCF in both of these is e to the 4x. And then so we're left with a 1 plus 4x equals 0. We'll pull out that e to the 4x. Then we can set each of these equal to 0. This first one is going to be nothing again because we try to take the natural log of both sides, and natural log of 0 doesn't exist. So it's nothing. This one is going to give us, looks like, negative 1/4. Right. And then so we'd plug that into the second derivative. So we need an f double prime. I would use this one here to evaluate. So it's going to be e to the 4x times 4 plus, now we do need a product rule with the second one. So 4 e to the 4x plus 4x e to the 4x times 4. All right, and remember, we don't have to solve this. We're just going to plug something into it, so it's not too bad. But let's clean it up a little bit. We get 4 e to the 4x plus 4 e to the 4x plus 16x e to the 4x. These two we can actually combine to make 8. So 8e to the 4x plus 16x e to the 4x. And then we can go ahead and plug in our negative 1/4. 8 times e to the 4 times negative 1/4 plus 16 times negative 1/4 e to the 4 times negative 1/4. That's going to give us 8e to the negative 1 minus 4e to the negative 1. So that would give us just 4e to the negative 1, or 4 over e. Now, actually, all we care about is if this is positive or negative. 4 over e is a positive number. So we can say we have a relative min at negative 1/4, comma. We need to plug the negative 1/4 into the original function. It's way up there. F of negative 1/4 is negative 1/4 times e to the 4 times negative 1/4. So we get negative 1/4 times e to the negative 1. So that's like negative 1 over 4e. All right. So some small decimal. Suppose you could verify this on Desmos, make sure we did it right. That is how it works. Okay. And one more, I want to show you a rational function. Works the same way. Just remember your quotient rule with this. F prime of x would be, take the derivative of the top first, so that's 2x times the original bottom minus original top times the derivative of the bottom over the bottom squared. Let's then just simplify a bit here. I'm going to go ahead and just distribute this because we got to solve it. We get 2x to the third minus 18x minus 2x to the third over, now the bottom I'm just going to leave as is. I'm not going to FOIL that out. And you'll see what happens here is the 2x to the thirds actually wipe each other out. So that's good. Negative 18x over x squared minus 9 squared. Okay, so now we can set this equal to 0. Remember, critical points occur where it's 0 or undefined, actually. So the best way to do this is just set the top equal to 0, because that would tell us where it's 0, and set the bottom equal to 0, because that tells us where it's undefined. So we get negative 18x equals 0. That just gives us 0. And x squared minus 9 squared equal to 0. We get x squared minus 9 is 0, so x squared is 9. And remember on this one that it is both plus and minus 3 when you take the square root. So don't forget that critical number. It's a very common mistake. So those are our 3 critical numbers. However, we do need a second derivative still. So I'm going to take this version of our first derivative because it's going to be way easier to differentiate. So f double prime of x, do another quotient rule. We get negative 18 times the bottom right, minus the original top, negative 18x. The derivative of the bottom uses a power rule where you got to bring the 2 down in front first. You keep the inside the same, subtract 1 from the exponent, and then times the derivative of the inside, which is 2x, over x squared minus 9 squared squared. So it's going to end up being the 4th power. All right. So we'll at least just reduce this a little bit to make it easier to plug our points in. Let's see. I'm not going to distribute, can't actually distribute into that first one, but I'm not going to try to do anything with that yet. Just combine some stuff, mostly with the second one. So it looks like we got a negative and a negative, so it become a plus. We got a 2, a 2x, and an 18x. So that's going to be, 72x squared? And then we got an x squared minus 9. And x squared minus 9 to the 4th on the bottom. And notice how all of these actually have an x squared plus 9 term and x squared minus 9 term. So I'm going to wipe this one out. I can wipe out one of these, and then I'll wipe out one of these as well, which is 3rd. Now we do have to cancel it from both of those top terms. So now we're left with negative 18 times x squared minus 9 plus 72x squared over x squared minus 9 to the 3rd. You could, I suppose, plug it in at this point. I'm just going to go a step further and combine some top there because we get negative. We can now distribute since that 2 went away. We get negative 18x squared. So we could just combine the 72x squared and the negative 18. So just do 72 minus 18. We get 54x squared minus 9 over x squared minus 9 cubed. All right. Now we can plug in our 3 critical numbers. F double prime of 0. Let's see, gives us negative 9 on top and negative 27 on the bottom. So negatives over negative makes a positive. That means concave up. So that is a relative min at 0 comma something. F double prime of negative 3. Let's see, that's going to give us a big positive on top. So we square it. And on the bottom, we would get, I think it's 0, right? Yeah, so undefined. Which means we actually have to use the first derivative test. That's not good. Let's try positive 3. I think we're going to get the same thing. Yeah, we're going to get, big number on top and then undefined on the bottom. Bummer. I don't know if I want to go through all right. Well, I got a class that's going to start pretty soon, so I might we'll abbreviate that part. So what we need to do is, for our first derivative test to check, what we have to do, f prime of like negative 4, see what that gives us, f prime of like negative 2, so we can see if there's a sign change. And then we could do f prime of 2 and f prime of 4. See if we have time to do those real quick. To our first derivative, looks like a negative 4 is going to give us a positive over a positive, so that's increasing. I think it would be the same. Positive over positive, so that's actually nothing if I'm doing this right. I'm trying to do it kind of quickly here. And I think it's same. This one would be a negative over a positive, so that'd be decreasing. And a negative over a positive, that'd be decreasing. So actually, I don't think there's any mins or maxes. These two. So our only one is there at 0, and then we do have to plug it into the original function still. F of 0, which is 0 over 0 minus 9, so it'd be 0. We did it. Sorry if that was kind of fast, guys. This, again, isn't difficult, but these last two with the e's and the rational functions can take a bit of time, but take your time with the derivatives. Do your best. Reach out to me if you do need some help. All right, see ya.